All right, we finally made it to solving these exponential and log things. So that's what we're going to do today. And just to recall, Pierre put some properties that you'll need to remember in order to solve. We talked about if a to the x equals a to the y, then x and y have to be equal to each other. So if we have the same exact bases, then our exponents have to be the same. If we have the same exact logs with the same bases, then the arguments have to be equal to each other. We'll use those one-to-one properties to solve quite a bit. And we talked about the inverse properties. If a to the log base a of x, then the a and log base a cancel and it frees that x by itself. And log base a of a to the x again cancels and just leaves that x. So we'll use that quite a bit to solve as well. So now we're going to talk about solving these things. And we're going to do it with and without a calculator. We'll start without a calculator. So if I'm solving an exponential that looks like this, we have 1/4 and we have 64. You've got to have the number sense to realize that 1/4 and 64 can have exactly the same base. And so we can get them to be the same base so we can set our exponents to be the same. 1/4 can have a base of 4. And so can 64. The 64 one, I think, is easier for students. They realize that 4 to the 3rd power is the same thing as 64. I have not changed the value of this equation. That's really important that you keep the value being the same. 4 to the 3rd power, though, is 64. So I replace this 64 with something that is the same value, but looks a little different. Same thing with 1/4. 4 to the -1 power would give me 1/4 because this negative flips it, and so it becomes 1/4. So keeping that same value, just making it look different. Anytime that we have a power to a power, we multiply. So this is 4 times -5x minus 1 up here in the power. And then on this one, it is 3 times 2x plus 3 in the exponent. Now they have exactly the same bases. So we can use this one-to-one property to set our exponents equal to each other. The reason why we do that is because now we can solve a regular equation you've been solving since way back in Algebra 1. We distribute to get rid of the parentheses, so I get -5x plus 1. I don't know why I just put the parentheses back there. And then we distribute the 3 there and we get 6x plus 9. So now we've gotten rid of our parentheses. We just need to get our x's together and our constants together. So I'm going to add this 5x to get it to the other side. And so we get 1 is equal to 11x plus 9. We subtract the 9 to get it to the other side. And I've run out of space, so I'm going to come up here. And that gives us -8 is equal to 11x. We divide by 11. And so x is equal to -8 over 11. And we've just done that without a calculator. This next one's a little bit trickier, but it's the same concept. And so when we talked about log properties last time, we said it's easier if we change these radicals to a rational exponent. So that's what I'm going to do first. So that would be 3 to the 1/3 power there. Now, in order to use that one-to-one property, I need one exponential on each side, and they both have to have the same base. So I need to put these together. Back in Algebra 1, we learned our exponent properties, and we learned that if you were multiplying two things with the same base, you add the exponents. If no exponent's written there, we know that's an exponent of 1. So we keep our base of 3 and 1 plus 1/3. And I'll show that off to the side for those of you that struggle a little bit with your fractions. That's what we're doing there is 1 plus 1/3. 1 is the same thing as 3 over 3. And so 3 plus 1 is 4. So we get 4/3. So on this left-hand side, we have 3 to the 4/3 power is equal to 3 to the x minus 5. Now that we have one exponential on each side of the equal sign, they both have the same base, we can set our exponents equal to each other. My last step would be to add this 5 to get it to the other side. And again, we're adding some fractions. So 5 would be the same thing as 15 over 3. So that would be 19 thirds is equal to x. All right, we've got 2 more down here. If you're feeling comfortable with it, go ahead and pause the video and try and do it yourself and then check your work. But we'll go ahead and switch these. For 4 and 16, they can both have a base of 4. They can also both have a base of 2. With 2, though, you would have to switch both of them, so it just makes more work. Try and do that base that they can both be with doing the least amount of work. So this would be 4 to the x minus 3. I didn't have to change it at all. This 16 would be 4 squared. And so I'd multiply the 2 times x plus 12. Now that they're both the same base, I can set my exponents equal to each other. And I'm solving just like I would in Algebra 1. I would distribute to get rid of the parentheses. I subtract the x to get it to the other side. And my last step is to subtract the 24 to get it to the other side. So negative 27 is equal to x. On this one here, the base that we can get both of those to be is 3. Therefore, I do not have to change the left-hand side. It's already got a base of 3. For the right-hand side, this would be 3 to the negative third. Remember that negative flips it. That's what's going to make it a fraction. So multiplying that negative 3 times x plus 4, which was my original exponent. Now that we have the same bases, we could set those equal to each other. So we get x minus 3 is equal to negative 3 times x plus 4. We distribute. And now we want to combine our like terms. So I'm going to add the 3x to get it to the other side. That's 4x minus 3 equals negative 12. We add the 3 to get it to the other side. So that is 4x is equal to adding that 3. So that's negative 9. And then I divide by 4. All right, now we're going to talk about solving some log ones. So those were some exponential ones we had to solve. Now we're going to talk about solving some logarithmic ones. And there's a couple different processes that we're going to do here. We have log base 4 of x plus 2 equals 3. In order to solve this one, I need to get the x out of the argument. The only way of freeing that x out of the argument is to change it to an exponential. So in this case, we're going to use that definition that we did on the first day there of logs to change it to an exponential. So we drop that base, so that's 4, and we switch these. So that's 4 cubed is equal to x plus 2. We've just made it easy to solve because we freed the x out of the argument. 4 to the third power is 64 equals x plus 2. My last step is to subtract the 2. And so we get 62 is equal to x. For this one, we have a number of different logs. So we need to do something different. We cannot use this definition to change it to an exponential because there's more than one log. So we're going to go ahead and combine these two. And so we used log properties to do that. We learned that with the log properties, if there's a plus in between both of those, then we multiply the arguments. We keep log base 3 and we multiply those arguments. So 6 times 3 gives me 18 is equal to log base 3 of x. Now that same property we were using up here with exponentials. When we had one exponential on each side and they were the same base, we can set our exponents equal to each other. Well, with logs, that one-to-one property right there tells us to do the same thing. If we've got one log on each side, so now we've got one log on each side, they're both exactly the same log, then this argument has to be equal to this one. So we get x equals 18. Now with logs, you do have to verify that the argument is not 0 or negative, because remember, those do not exist. If you think back to the graph of the log, it looked like this. There are no negatives and there is no zero since that's my vertical asymptote. So the argument has to be positive in order for it to be a true solution. So this one here is a true solution. All right, we're going to try a couple more. Again, I use my log properties to condense that. So I keep my log base 3. This is separated by subtraction, so I'm going to get 5x plus 13 over 6. I'm dividing because of that minus, equals log base 3 of 3x. Now that we've got one log on each side, I can go ahead and set the arguments equal to each other. So 5x plus 13 over 6 is equal to 3x. In rationals, we learned that you can cross multiply to solve this. So that would be what I would do to solve this. 3x times 6 is 18x. 5x plus 13 times 1 is just 5x plus 13. I subtract my 5x. And so we get 13x is equal to 13. I divide by 13. My x is equal to 1. Again, I verify that that has not given me a solution that doesn't work. If I plug in the 1 here, it is going to be a positive. If I plug in the 1 here, it is going to be positive, so that works. All right, for this one here, again, I would have to use the log property to make sure that I have one log on this side so I can use the definition. So I'm going to use the product property, the power property here to get that up here so that the log is by itself. So I get log base 4 of 6x to the 3rd power is equal to 9. Now I'm ready to go ahead and use the definition. 4 to the 9th power equals 6x to the 3rd power. On this side, I'm going to go ahead and distribute that cube to both of those. So that's 216x cubed. For 4 to the 9th, I think I'm going to have to use the calculator on that one. 4 to the 9th power gives us 262,144. We divide by 216. And that gives us 1213.63. I did round a little bit there, but you do not want to round until the very end. So when I do the cube root now, that's what we're going to do to get rid of that x cubed. I'm going to take the cube root of both sides. When I take the cube root, I go to math, and then my cube root. And then I want to arrow up. So I'm going to use the arrow key to highlight that part there and hit enter, and it will copy and paste that for me so that I'm not rounding until the very end. I then hit enter, and x is 10.666 repeating. So I keep 3 decimals. Some of you might be thinking, what is that squiggly line? Remember, that means approximately. All right, so we've got another one here that's separated by minus again. So we're going to do division in the arguments. And so we get log of 5 plus x. And I'm going to go ahead and write that with the x first because I don't really like having the x second. So that's x plus 5 over x minus 3, because that's the other argument, is equal to log of 5. Now that we have the same log on each side of the equal sign, and it's just a single log, we can go ahead and set each argument equal to each other. So x plus 5 over x minus 3 is equal to 5. We cross multiply, so we get 5 times x minus 3 is equal to x plus 5. We distribute. I subtract my x to get it to the other side. I'm going to add the 15. For x is equal to 20. And so I divide by 4, and x is equal to 5. I checked to verify that that doesn't make anything undefined, and it does not. All right, so we're going to come over here. This is separated by a plus. So I'm going to keep the common log, which is the base of 10 one, and I'm going to multiply those arguments. And now we're ready to use that definition. There is not a log on each side here, so we can't set the arguments equal to each other. In order to free this, I need to use that definition to change it to an exponential. So I drop my base of 10, because remember the common log has a base of 10, and I get 10 to the first power is equal to x times x minus 9. When I distribute this, I end up with a quadratic. And we know how to solve quadratics. We set them equal to 0 so that we can factor. So I'm going to subtract that 10 to get it to the other side, and we get x squared minus 9x minus 10. I factor. X times x gives me x squared, and then I'm looking for what multiplies to be negative 10 and adds to be negative 9, and that is a negative 10 and a positive 1. So my two solutions here are 10 and negative 1. That's what makes each parenthesis 0. Now, when I go back and I plug in this 10, it will be positive in both of those arguments. So that works. So that's the solution. However, when I plug in this negative 1, it causes a negative in the argument here. And we know that is undefined. You cannot have a 0 or a negative in the argument. This is considered an extraneous solution. So we would not consider that an answer. 10 would be the only answer. If given a multiple choice question, 10 would be the only answer. If it said 10 and negative 1, you would not want to pick that. The negative 1 is a solution to this quadratic, but it is not a solution to this log. All right, for our last one here, again, they're separated by a plus, so I'm going to multiply the arguments. In this case, again, we have to change this to an exponential, so I'm going to drop the base of 5. I raise it to the first power since those two switch, and so we get x plus 6 times x plus 2. Again, we're going to end up with a quadratic because I'm going to FOIL this. So we get x squared plus 8x plus 12. I need to subtract the 5 to get it to the other side. So we get 0 equals x squared plus 8x plus 7. That factors to be x plus 7, x plus 1. And so our solutions are negative 7 and negative 1. And this one looks tricky because you guys want to say both of those don't work because they're negative, but that's not true. If I plug in a negative 7 here, it does make this negative and it does make this one negative. So this is considered an extraneous solution. But if I plug in the negative 1 plus 6 is 5. So that argument is still positive. If I plug in a negative 1 here, negative 1 plus 2 is 1, again, a positive number. So this works. That would be one of my solutions. What we care about is if the argument is 0 or negative. So some things to remember. The argument can't be 0 or negative. Those points are undefined, so you want to make sure that you know how to do that. In order to set the arguments equal to each other, there has to be a log on each side. So a single log on each side to set equal to each other. That was solving exponentials and logs.